Oh, hey guys. In this video, we're going to learn about Faraday's law of electromagnetic induction, which won't actually have very much to do with this permanent magnet, but will have a lot to do with electromagnets. Okay, sounds awesome. Here we go. This right here is Faraday's law of electromagnetic induction. Might not look like much to you, but it ends up being important for all kinds of things. And for that matter, is the answer to about 100 years or a half a century, something somewhere in that range. I'm not a historian. Of an answer to a question which had been sort of bugging scientists for a while, which went like this. We know, and they had known for quite some time, since like the 1800s, that a current going through a wire would produce a magnetic field around it. And they were able to describe the shape of that field and everything else. And we learned in a previous unit that this is the formula for that field. Wonderful. All right, now the question though was this. If a current can make a magnetic field, can a magnetic field make a current, right? Meaning if it goes this way, does it also go back the other way, right? If a current can make a magnetic field, then it should make sense that a magnetic field ought to be able to make a current. The trouble was that nobody could figure out how to make this work until Michael Faraday came along and actually almost accidentally discovered exactly how it does work, which is to say his law of electromagnetic induction. So what I'm going to do for you in this opening part here is show you, reenact for you somewhat anyway, Michael Faraday's sort of first experiment that confirmed that electromagnetic induction was a thing. So here's how it goes. I have before me a voltmeter, okay? And I have also this system right here, which looks like a mess of wires and stuff, but here's what it consists of. We have a coil of wire. We have another coil of wire inside of it. Right. Faraday didn't use exactly the same setup. He had like a metal donut and then like wire wrapped around it. Okay, it's approximately the same idea. And then I've got this iron core here, mostly just to make the magnetic field a little bit stronger. Okay. All right. Now, right now there's no magnetic field because this is presumably copper wire, not a magnetic material. But down here I have a power supply. And what I'm going to do is I'm going to turn it on and turn it off and turn it back on. All right, and when I turn it on, there will be a magnetic field produced by this coil of wire, which if you recall is called a solenoid. When this has a magnetic field going through it, there will also therefore, has a current going through it, and it makes a magnetic field in this inner region, which is where it makes a strong field. This solenoid will be in that field. All right, and we're going to see then what happens on the voltmeter when I turn the current in this outer solenoid on. All right, so watch the needle. It bounces around a little bit because, of course, I'm holding it and moving, but I'll try to hold it steady. Here we go. I'm about to turn the current on. Whoa, it moved. But now it's not moving anymore. All right, now, of course, you can't see it, but there's current flowing through the wires. But nothing's happening. So there's current flowing. Something happened right when I turned it on, but nothing is happening now. All right, well, I guess I'll turn it off. It's probably broken. And oh my gosh! The needle moved so much. Oh, well, okay. So let's talk about that. This puzzled Michael Faraday a little bit too, because that's exactly what he observed with his experiment was when he turned the current on, something happened, right? He got suddenly a voltage appearing. And when he turned it off, he got a voltage appearing. But while the current was just steadily running through the wire, nothing was happening. So this is a weird result, but ultimately what he realized was a magnetic field would only produce a current in a nearby wire if that magnetic field was changing over time. So at the very moment that he turned it on, there was a massive change in the value of the magnetic field in the area of that second solenoid. All right, fine, there was a sudden change in the value of that magnetic field, But then once the current was on, it was on, and there was no more change. All right, when he turned it off, same comment, right? Suddenly there was no field, so there was a massive change in the field. And it turns out to be that that change is what makes the EMF, the voltage, the current, appear in the other object, okay? All right, so then that is, in a nutshell, Faraday's law of electromagnetic induction. All right, I'm going to try to explain exactly how we understand this to work in an animation, because from this we lead into something called Lenz's law. All right, but before I get to Lenz's law, we need to talk about exactly what this thing is right here. Because note, this doesn't say like rate of change in the magnetic field. It says rate of change in funky Greek letter. All right, so this funky Greek letter, if you recall, is a capital phi. It represents flux. There's two kinds of flux that we ultimately talk about in physics, at least only two that I know of. Electric flux, which we use for Gauss's law. And then there's magnetic flux, which is what we talk about for Faraday's law. So sometimes you'll see this flux symbol with a little subscripted B to represent that it's the magnetic flux specifically. Okay, flux. What was flux? Flux is what you get when you do a field of any kind times a surface area. Specifically, though, remember, it's going to be a dot product of the magnetic field vector and the surface area vector. All right, now, if you're hazy on what a surface area vector is, because that is kind of a little bit of a weird term, if we were looking at a magnetic field going through this piece of paper, right? Turn it like this, right? Here goes the field through the piece of paper. The surface area vector would be perpendicular to this surface, so it might point straight out that way, okay? All right, so the surface area vector always points out from the surface. All right, so therefore, if you have field lines going, say, directly in or out of a surface, that's when you have the maximum flux, right? When they go in like that, because you have surface area vector, magnetic field vector, and they are parallel. Well, actually, I've done anti-parallel here, so whatever, parallel, all right? The reason that gives you, of course, the maximum flux is, recall, that a dot product is proportional to the cosine of the angle between the vectors. So therefore, you get a maximum flux when the field and the surface area vector are parallel. All right, you would get a minimum field, minimum flux, meaning zero flux, when it looks something like this, right? The field lines are just brushing the surface, right? Not going into it like this, right? They're just brushing over it, and then you get zero flux. All right, now what Faraday discovers, of course, is that it's not so much the flux that is important in and of itself, it's the rate at which that flux is changing. But there's a lot of different ways that you can change the flux through a particular loop, or whatever you have flux through, okay? So here are the three major ways you can change the flux through something, and then we'll bridge from that into talking about Lenz's law and what that tells us about the direction of the current that's going to exist in a loop or region in your magnetic field. Okay, so here goes. Way number one, this is called motional EMF. I don't know why I'm starting with this one in particular, but it's, I think, the one with the most straightforward formula, all right, or at least the most stereotypical formula. It goes like this. Let's say that you have some setup like this, and there's a magnetic field in here. Great, magnetic field, wonderful. All right, and then we have a bar that is like a sliding contact on these, right? So this bar can slide up, it can slide down, all right? And of course, as it slides, since it's a metal bar, it's going to complete, complete the circuit, electrically speaking. All right, now we haven't drawn in a battery or anything like that. That's okay, we don't really need one. The point of this is that Faraday says that as this bar moves, it's going to produce an EMF. So even though there's no battery, it'll be like there is one because current will begin to flow through this system. All right, so here's what that looks like. As this falls, the loop that's being defined is right here. It's just this, right? That this is where current could flow. This is open at the bottom. It doesn't have to be open at the bottom, but often it is, okay? So if we're looking at this area right here, as this bar falls, the A in the magnetic flux formula is changing. All right, so that's usually how motional EMF works, is you're changing the area of a system by sliding something up or down. It doesn't have to be a box, all right, but talking about like an expanding ring is kind of goofy, right? So usually something like the falling bar is what kind of makes it work, most easily anyway. All right, the flux at any given moment, of course, is, well, B times A times cosine theta. We're not going to worry about this in this circumstance because I have that coming out, going in, right, parallel to the surface area vector. So it's just going to be B times A. Don't need to worry about the cosine. This dimension is L. This would be W, I guess. All right, so the flux is BLW. All right, but nobody actually cares about the value of the flux. That's not of itself important. What matters is the rate of change in flux. So if I want to know the EMF and ultimately the current that's going to be produced in this loop right here, I got to take the derivative of that. In order for there to be a derivative, something has to be changing over time. So if you imagine this as being like, again, vertically oriented so this bar can fall, W is the dimension that changes with respect to time. Well, how fast is W changing? I don't know. How fast is the bar falling? That's the answer. The rate of change in W is the speed of the bar as it is falling downwards. So B and L are constant, and dW dt is the speed as it goes. So therefore, the rate of change in flux is BLV. Mr. Erico, what about the negative sign? That's actually going to come in when we're starting to think about the direction that the current flows, which again, that's going to be a reference to Lenz's law, which goes back to whatever. They go back and forth. They're related concepts, but I'm not going to worry about the negative sign and what exactly that means in this video. I'll continue that thought in another one. But as far as what's the EMF that's going to be induced in this, right, whether it pushes current clockwise or counterclockwise, right, the amount of current is going to be based on this EMF and whatever the resistance of all the various wires are. All right, so very commonly then you will have motional EMF, and always BLV is your EMF. All right, here's the next possibility. We could have, I don't know, a similar setup, or we could have a loop or whatever. This is where you have a changing field. All right, let's draw dots this time, just for variety. If that field is increasing or decreasing, then there's going to be a change in the flux. And so in that circumstance, the flux is just BA, and therefore the rate of change in flux will be dB dt times A. All right, so you need a function for the magnetic field with respect to time. Okay, and then that times the area is going to be your induced EMF. All right, last possibility is you spin the loop. If we are rotating a loop in a magnetic field, as it spins around, the flux through that loop is changing, right? Magnetic field is in a constant direction, If the loop is rotating as it goes, then it's the cosine theta part of the flux equation that's changing. All right, depending on the angular velocity with which it's spinning, right, whether it's slow or fast, right, you're going to get a different rate of change in the flux. So you have to express theta as a function of time, which I've done here. If you can't read that, it says theta equals omega times t. Omega, of course, being angular velocity. So as this spins around, right, or excuse me, it's technically angular frequency, but whatever. That's a subject for actually literally a different video. You take the derivative of your flux equation, right, BA cosine omega t. Because of chain rule, this omega ends up out here. So now we have the negative derivative being BA omega sine omega t. So if you spin the loop faster, you're going to get a larger EMF induced in it. All right, now an interesting side note about the spinning the loop thing. This is actually how electricity is commercially produced pretty much everywhere in the world, right? Things like your laptop and maybe a power drill might run on batteries, okay? But most things, right, anything that plugs into a wall runs on what's called alternating current. It's called alternating current because the current goes back and forth. Batteries produce only direct current, right? Goes one direction. That's what it does, right? Whereas alternating current goes back and forth. And the reason it does that is because of how the flux is going to change here, right? It works according to a sine function, and the flux is according to a cosine function. The EMF is the derivative. Anyway, you will get a sinusoidal function, right? So at some times the flux is increasing, at others it's decreasing, and the result then is going to be that you will get an EMF, which is changing not only magnitude but direction. And the result then is that current will go both ways inside of a wire. Not at the same time, but you know. Okay, next up is Lenz's law.